Hello everyone, my name is Fatih Ilhan and I will present our work, Adaptive Deep Neural Network Inference Optimization with EENet. Adaptive inference with early exiting leveraged observation net. Some examples can be easier to predict than others. So these multi-exit models can adaptively stop inference at runtime with one of these early exits based on certain confidence measures and thresholds. When we look at existing work, they mostly focus on designing specialized architectures, specialized multi-exit architectures that have good performance in early exits. And there are studies on enhancing the training of these types of models. But they still consider heuristics-based confidence measures such as maximum score, entropy, voting, and hand-tuned thresholding. So the question of what is really easy for that model, or how should we compute those thresholds based on a given budget, this remains as an open problem. So EENet tackles this problem by bringing an early exit scheduling framework, enabling optimizing early exit schedulers given the inference budget. So we first introduced the concept of exit scores, combining multiple confidence measures and also classifies prediction scores. So instead of using manually defined scores, we also optimize exit scores. Second, we optimize the distribution of samples to different exits and compute exit thresholds after finding that distribution, given the inference budget. So instead of hand-tuning, manually finding the thresholds that satisfies the given budget, we also optimize that as well. And these optimization steps are all performed on the validation data set. And this is decoupled with the training of the multi-exit model. So this also helps us to quickly adapt to varying dynamic budget scenarios because we don't have to train this model or fine-tune this model from scratch whenever the budget changes, right? So we only train the schedulers. We performed experiments on image classification, semantic segmentation, and text classification datasets. And compared to existing approaches, EENet consistently outperforms with speed gains up to 2 times under negligible performance degrees. So now I will start talking about our methodology. The first step is training this multi-exit model, right? So after injecting these early exit classifiers to certain exits, we have a joint loss optimization for the training of these early exits, and the final exit also changed. So the total loss is a weighted combination of the losses at each exit plus a self-distillation loss. Here, we also use a technique of self-distillation to improve the performance of early exits, right? Normally, they perform significantly worse than the final exit, but with self-distillation, we treat the final exit as the teacher and the early exits as the students, and also minimize the KL divergence, which encourages early exits to have as similar as possible predictions to the final exit, even though they have less layers to pre-process data. This improves their performance. In the next step, after having trained this multi-exit model, we will start optimizing the inference stage, right? So the first question was how to measure the confidence on a prediction. So there are rule-based approaches like entropy, where high entropy means low confidence, and some studies just use the maximum score as the confidence, or patience-based scoring. And second question was how should we find the exit thresholds to make those exiting decision, right? So at EENet, we will try to utilize the available data to optimize these exit scores and thresholds. So the ultimate goal will be learning an early exit scheduling policy optimizing some early exit scoring functions and some thresholds that maximizes the overall validation accuracy while satisfying that the cost of the process will be less than the given budget. So average latency per sample will be less than the given average budget per sample. So here the budget can be defined based on number of flops or latency. We consider latency because it's more practical in the practical applications, right? So to do that optimization, we first define two target variables. First one for the exit scoring and second one for the exit assignment. So QK is basically, it represents whether a prediction is correct or not. So we will try to estimate these with the exit schedulers, and our estimations will be basically the probability that output, the prediction was correct. So this is the first target variable. And this is the first target variable. As you see, at each exit scoring functions will try to predict that prediction was correct or not indeed. And the second target variable is the exit assignment variable. Here we denote it as RK and use it to represent the, if we consider like the exit index as a random variable, this will be the posterior probability of the exits variable. So RK will be modeled using the predictions of QK. So it is basically not something we have for a given sample. We don't have like, this is the correct exit you should exit. So we use this, we introduce this intermediate variable, which will be used in our optimization. And for the prediction of those, for the QK, we just use a linear transformation. Here, inputs are the prediction vectors, prediction vector, confidence vector, which encapsulates different confidence measures, and also the exit scores computed at previous exits. And this linear transformation in the end will give us probability that that sample, the prediction for that sample was indeed correct, given the prediction vector and the exit index. So this is the exit score we will use. And for the exit assignment prediction, we have the same set of inputs, but the HKV, instead of one layer, we use two layers. And we also optimize the outputs with the softmax. So in the end, the output of these softmax will give us the posterior distribution, the predicted posterior distribution of the exit index, exit random variable. So the next step will be optimizing these functions. For this, to this end, we consider a joint iterative optimization. So as you realize, like RK depends on QK hat. So there is a relation. So we are not jointly optimizing them at the same time, but we optimize them iteratively. So for the exit scoring functions, we have basically a two-class classification problem. So we have a weighted binary cross entropy loss, where these weights are based on survival probabilities and encouraging each function to specialize in its respective subset of samples. So these exit scoring function basically will receive more loss from the samples that are more likely to exit at that exit. And for the exit scoring functions, we have a combination of KL divergence between predicted posterior and the target posterior distributions, and also a budget loss, which is defined as a scaled mean absolute difference between the budget and the resource usage. For more details on these theory, you can check our paper. And after optimizing these functions, okay, we have our exit scoring functions, exit assignment functions, but now we want to compute the thresholds. So please note that we are still working on the validation data. We're not doing tests. So here, For each exit, we first filter out samples with the highest scores until the assigned quota for that exit is full. Here, assigned quota will depend on the exit assignment scores. And after exiting those samples for that exit, we treat the final, the exit score of the final sample as the threshold. And we repeat this process for each exit and we compute the threshold. This is the pseudocode for the algorithm. And okay, we have our exit scoring functions and thresholds. When it comes to inference, we will just use those. So during test, what we will do is at each exit, we will use the exit scoring function to compute the exit score. And if it is greater or equal than the threshold, then we will exit. If not, we will continue. And this will be the early exiting inference stage, which we will be using for the evaluation on test data. So to evaluate our model, we consider comparisons with 4 existing methods, with 5 models on 6 different datasets. We performed experiments on image classification and segmentation. So here you see the results at Cypher10, Cypher100, ImageNet, and Cityscapes datasets. These are their base model latency values, and these are the performances at different budget scenarios. The top row is for the easier budget scenario, and bottom row is stricter budget scenario where you have less budget. You have more speed gain, but you need to exit earlier for more samples to satisfy this budget. And we observe consistent improvements, especially when the budget is tighter. We perform up to 5% gains with EENet. For the text classification, we have 2 datasets. We performed similar experiments and we observe significantly better results actually. And here, in general, as we will show you, we see that EENet can use early exits more efficiently. So here there are some samples, visual samples. Here, visual comparison of the outputs of MSDNet and EENet. And detailed explanations are in our paper, but you can see that for some samples, EENet exits early and still gets the correct output. For some samples, EENet exits late, but gets the correct output, whereas the other approach cannot. There are different scenarios where EENet actually performs better. And for the segmentation, what we see is usually if there are more objects, like more people, more occlusion, like if there are more challenges in the frame, we observe that the model tends to not exit. But if there are like less objects, if it's more background, then the model usually early exits. And we also analyzed why and how our approach works well. So first we look at the exit scores. So how it changes when we just look at the maximum prediction scores or the exit scores with EENet. So when we look at maximum prediction scores, here you see that for certain classes, especially the classes with low success, the correct predictions, even though they're correct, they tend to have low scores. So when we just apply thresholding, same thresholding for every class, you tend to miss a lot of opportunities there. But with EENet, exit scoring functions helps us to calibrate the scores across classes, enabling us to solve the issues related to statistical differences, right? So even though these are low success classes, the correct predictions have still higher scores, which in the end works better when we just apply one threshold, and this will not prevent us from losing those opportunities. We also analyze the weights of the exit scoring function, we see that the maximum score has the most impact. But like there are different weights at each given to each class. Basically, we observe that there are higher weights for low success classes, which helps us to achieve this effect. So, as I said, this actually calibrates the score of the exit scores. We also performed ablation studies, observing how optimizing distribution or optimizing scoring helps us to achieve good performance. And both are really important factors. So just optimizing exit scores or thresholds is not really enough. Optimizing both is best approach. So this is all for my presentation. Thanks for your time. If you have more questions, please visit my poster session or read the paper. Thanks for your time.